Okay, so let's probably get started. Welcome to the third lecture of the 6th week. We are halfway done. And before I start, I would like to make an announcement that next week we'll have Melbourne Connect Innovation Week. There will be a bunch of interesting talks about AI, about technology, science, and everything. So it will be happening in Melbourne Connect, right across the Swanston Road. So you can come for free. So it's just maybe requires some registration, but you can just visit this website, it's innovationweek.melbourneconnect.com.au, and you're more than welcome to come for the events there. So, and today is August 30th, so it's almost the end of the winter, hooray. So what happened on this day in history? So in 1574, Guru Ram Das became the fourth Sikh guru or master. In 1835, in Australia, Melbourne was founded. Hooray! We should celebrate this. In 1873, Austrian explorers Julius von Payer and Karl Weierstrass discovered the archipelago of Franz Josef Land in the Arctic Sea. And 1945, the Japanese occupation of Hong Kong came to an end. In 1995, in terms of Bosnia War, NATO launched Operation Deliberate Force against Bosnian Serb forces. Okay, so, and what's our agenda for today? So we have an advanced lecture about object-oriented paradigm. So we'll discuss what this paradigm is, the general principles behind the paradigm, and then I will provide some example how you implement a class in Python. So as we mentioned before, so programming is an art, so you still kind of create a model over the world, some aspects of the world, and you can approach the same problem from very different perspectives. So, and programming paradigms, they set the way you think about that particular problem, the way you approach and conceptualize it. So, and again, as we mentioned before, the same problem can be conceptualized in very different ways. You can approach it from very different perspectives. And there are many, many different programming paradigms. These are just the most popular ones. So, for instance, there is functional paradigm where programs are treated as math functions. This paradigm is realized in programming languages such as R or Lisp, and partially in some languages like Python, such as lambda function or recursion. So the next one, most common, is called procedural. So it's step-by-step iterations where common tasks are placed in functions that are called as needed. The next one was very popular in the 1980s. It's a logic paradigm, so it follows the formal logic. And any program is just a set of sentences in logical form. So Prolog is one of those programming languages that realizes that particular paradigm. And related to that, there is a symbolic paradigm where the program can manipulate its own formulas and program components as they were plain data. So this is realized again in Prolog and Lisp. And finally, the most common nowadays, or at least like the early 2000s, it's called object-oriented paradigm, where the basic concepts are objects and classes. So objects have this data, so those attributes and properties and classes, and they also have the functionalities, so-called methods. So this object-oriented paradigm is realized in languages such as Python, C#, Java, C++, etc. So, and now the big secret behind Python, that in Python actually everything is an object. So, for instance, here, so we assign the value of 5 to the variable a. And then when we ask what type are you a, the answer will be that it's a class. You will see this word class here. So it's a is an instance of the class integer. So there's the general notion of class, and a is an object of that class, a particular realization of that class. And when you look at pretty much anything in Python, so you can look at the Python sources, you will see that everything is defined as a class. For instance, there is a special module called CSV that provides the functionality to work with CSV files. Who knows what CSV file is? What is this format? Yes? Yeah, sort of like a spreadsheet. It's comma-separated values, right? So we just provide all our spreadsheet values separated by commas. Sometimes they might be also separated by tabs. So it's sort of like a particular format of the file. So for Python, there is a special module to work with such data format. So, and there is a special class in that module, inside of that module, which is called dict reader. So it's dictionary reader that takes this file and reads this particular format, processes it. So you can see that it's realized as a class. So if we now go to the sources of Python, so we'll see this is a class. So here is an example, so dict reader, and it has a bunch of functions, so like class-specific methods. Okay, and similarly, there is also a dictionary writer. So dictionary reader reads the file, dictionary writer takes some data and writes this data into that file in that particular format. So again, if you look at the sources in Python, you will see that it's just a class. So, and what are the core ideas in object-oriented paradigm? So as I mentioned, so there is notion of a class. So class is an abstraction. It's sort of like an abstract entity. An object is an instance of a particular class. It's a realization. So if you think about, for instance, university and students, so we can introduce some abstract notion of a student. We can look at all particular students and find what are the common properties of the students. For instance, all students have first name, last name, date of birth, etc., right? So we can define an abstract entity called student that will have first name property, last name property, date of birth, and they also do something, right? Students, they enroll into subjects, they graduate, they take exams, so that will be our functionality. So we'll define methods for this abstract kind of entity, student. So class is just our kind of thinking about this abstract entity. And then when we create an object of that class, it means we create a particular student, for instance, John Smith. So, and so each problem in this paradigm can be conceptualized in terms of classes. And again, class is just an abstraction. It's an abstract, it's a model, right? And then we realize this model, this abstract entity as a particular object. So a particular student whose name might be John Smith. And again, each class has some data that we would like to store. So that might be for student, I guess, as I mentioned, like first name, last name, etc. And some functionality, the methods, what our students typically do. And yeah, objects instantiate the class. So class is just very abstract. So an object also encapsulates a specific logic of processing of relevant information. So it has some private data, and it also has some interface to interact with other objects. So send the request. This sends the request response. So, and we expect that object of the same type should process the same request similarly. But in addition to that, because our world is structured hierarchically, so our classes will also be structured hierarchically. So we can inherit one object from the other objects. So, and this leads us to the three whales of object-oriented paradigm. So in the early 2000s, if you apply for a software developer position, you would most likely be asked about these three whales of OOP. So what are those three core principles in object-oriented paradigm? So First is called polymorphism. So poly means many, morph means form. So it's multiple forms. So it means a single interface for entities of different data types. So the second one is called inheritance. So child classes inherit data and behaviors from parent classes. So, and finally, encapsulation. So we do not provide everything about the object, but we provide some interface to interact with that object. So let's go through each of these principles one by one. So polymorphism. So similar to say like people greet each other, they might greet each other in different languages, so they still have a single, say, method called greet, right? But this method might be realized differently depending on your native language. Some people say hello, some people say namaste, some people say ahoy, etc. So we have, if you want to implement a class about, like, say, human and they speak, so we'll have a single method greet, but it will be realized in a different way depending on the language. And when we think about Python, so you see that a great example of this particular principle is the function print. So you call the same function regardless of the data type. So it works for most of the data types that you have in standard Python library. So for instance, it may take the string as an argument. It may take integer or float or Boolean value. So you use the same interface. So it's always just print function. You don't call print string, print integer, print float. You do not think about this. You just know that you need to use this print function if you want to print the value of some particular data type. It's just a single interface, and it provides the same output for different data types and different scenarios, right? So this is called polymorphism. So another example is, for instance, you would like to open some file for reading. So you use this function open. And you use the same function regardless whether it's a text file or if it's a binary file. So you just use the same interface. So for you as a client, it just looks exactly the same function. But if you then put the result in some variable and ask what type are you, my file, you will see that actually internally it's very different data type. It's an instance of different classes. So one, in the first case when you process text file, it will be text IO wrapper. In the second case, it will be buffer reader. But again, you just use the same function. You don't have to use open text, open binary, etc. You have the same open function. But the resulting data type will be different. So this is polymorphism. Another crucial principle is called inheritance. Because our world is structured hierarchically, you can think of, for instance, animals, and there are different types of animals, reptiles, mammals, etc. There are different types of mammals, such as cats, dogs, cows, right? These cats and dogs, they share some properties, right? And those properties are shared with animals. So we don't have to specify all these properties like that cat eats and dog eats. Cat sleeps and dog sleeps. So we don't have to specify for each type of animal. We can specify the shared property on this parent class. This is called parent class animal. Because we expect that all animals, they have this functionality. They can sleep, they can eat, they can do something else. So we will have this animal as our parent class. And from that, we will inherit all these particular types of animals, and then we can extend their functionality, saying like, okay, cat meows and dog barks. So by using this inheritance, we can define these shared properties on the parent class, higher level of abstraction, and then inherit it, reuse them in the child classes. So similarly, if you think about this geometric shapes, you can also think about this hierarchical relationship. So we have like the most abstract shape. If we look at these quadrilaterals, it will be this quadrilateral. And then when we apply certain restrictions, we, for instance, require two sides to be parallel to each other. We get trapezoid. Then the parallelogram is a special case of trapezoid where we require all pairs of sides to be parallel. And from parallelogram, we can either get rectangle by requiring all the angles to be the right angles, or we can get a rhombus by setting up the restriction on this, having all the sides of the same length. And the most specific case will be a square, right? So square, in this particular case, it's inherited from rhombus, in the sense that it has all sides of the same length. And it's inherited from rectangle. So meaning that it has this right angle requirement. So it's still a square is a special case of this quadrilateral after we apply certain restrictions, right? So we can implement these particular structures, this nested class structure. So we have the most abstract class, which is quadrilateral. We might have some functions such as draw quadrilateral. And then from that, we will inherit trapezoid. Then from trapezoid, we can create parallelogram. And from parallelogram, we can create either rhombus or rectangle. And then square will have both rhombus and rectangle as the parent class. So this is about inheritance. The next core principle is called encapsulation. So it relates to containing information in an object exposing only selected information. So when we define a class, we also define the interface for this object of that class to interact with other objects. So we probably don't want to have all the data to be public, right? You can think about this analogy with the car. So the car has this sort of like public interface, which has a steering wheel, gas pedal, and so on, right? But it has some private properties or data. For instance, the engine elements. So when I drive a car, when I want to switch on, I definitely do not go and check each particular element in the engine. I just use a particular part of the public interface. Or when I drive a car, I just use the steering wheel, right? I do not go and fix the engine elements because I can just break it if I access the engine directly, right? So the steering wheel serves as my public interface to this functionality of the car. But I have still this internals of the car, internals of this engine part, right? So this will be our private class data, and the steering wheel gas pedal will be our public interface that we provide to interact with the objects of that class. So those are three ways of object-oriented paradigm. So, and later on, they were further developed in more like fine-grained principles. Those are called solid principles. Nowadays, if you come to this job interview, you might also be asked about the solid principles. So solid is an abbreviation, so it has this single responsibility principle, open-close principle, Barbara-Liskov substitution principle, interface segregation principle, and dependency inversion principle. So let's go through each of them one by one. So single responsibility principle, what it means. So every class should have its own responsibility. So suppose you are creating a kind of class to describe, or like application to describe university, like LMS. So it would be an extremely bad idea to have a single class called university and include like students into that class, include all the lecturers, all the administration, all the subject, just put all the possible functionality inside of this, the most abstract class called university. It's an extremely bad idea. So, so this is actually this principle that states that you should not create a single godlike object that does all the functionality possible for your problem. So you need to modularize, right? So you need to identify what entities are there. That there's university has subjects, it has students, they have some staff, some of the staff is lecturers, some of the staff is administrative staff, etc. So you need to identify all these entities. So, and each class should have its own responsibility. So, and each class and object, they should be specialized. So again, it's one of the core ideas of programming. You need to decompose. You need to learn how to decompose a problem into sub-problems and identify all these entities. And relevant to this, I wanted to quote Dijkstra, who is a famous person from computer science, who put this paper on the role of scientific thought. This is also the way scientific thought works. So scientific thought comprises intelligent thinking as described above. Scientific discipline emerges with the usually rather slow discovery of which aspects can be meaningfully studied in isolation for the sake of their own consistency. In other words, with the discovery of useful and helpful concepts. So the second one. So it's called open-close principle. Software entities should be open for extension but closed for modification. So what does it mean? If you have, for instance, a car, and now you're creating a supercar, right? So this supercar should still have the functionality of the car. If the supercar lacks steering wheel, you're in a problem, right? If you allow for the supercar to kind of eliminate steering wheel or gas pedal, you'll have the problem. The driver will not know what to do, right? So, so if your car is the parent class, so the supercar can only extend it but not modify the pre-existing functionality essential for that particular class car. So, for instance, if you have a supercar, so again, it's expected to have the functionality of car. It is expected to have steering wheel, gas pedal, etc. But you may add, for instance, object detection or some computer vision component into it. So, and the public interfaces should not be open for modification. So you can only extend. So if you inherit from that parent class car, you can only extend, but not modify the pre-existing functionality, because otherwise someone who uses that, they will try to, for instance, access steering wheel in the supercar, but there is no steering wheel at all. So the next one is called Barbara Liskov substitution principle or subtyping. An object such as a class and sub-object such as class that extends the first class must be interchangeable without breaking the program. So if you go back to this example with this open, so for the user, it's just a single interface, the function open. But if you look at the internals, you see that it's, there are different classes that process this particular request, right? But for us as a user, it's the same interface. But internally, there are different classes. You get the objects of different classes. So, so a child class should provide full functionality of its base class, and user should not notice that the child class is called. For instance, you can think about the electrician and an apprentice of the electrician. So if something is broken in my apartment or house, I call electrician. But electrician might call the apprentice. And when apprentice comes and fixes, I should not notice the difference in the quality and the difference in the result. Okay? Okay. So the next one, interface segregation principle. So Many client-specific interfaces are better than one general-purpose interface. It's related to the very first principle. So you should not try to create sort of like this Swiss knife or like godlike class that does all the possible functionality. So it's a bad idea to have a single interface for everything. So you try to make sure you have the specialization. You account for the specialization. So there is always a trade-off, right? So one is like, in the one extreme, you have just a single class managing all the possible scenarios. In other extreme, you have many very, very kind of scenario-specific classes. For instance, you can come up with all this like open binary, open text, read binary, all these like multiple subclasses, sub-interfaces, and it will be extremely confusing. So you need to find a good trade-off between these two extremes. Not to be too general, not to be too specific. So, and finally, dependency inversion principle. So depend upon abstractions, not concretion. So you first, when you develop something, when you think about conceptualization of a problem, you start from the abstract classes. You try to come up with this sort of like more abstract entity. And then you inherit from them. So you come up with this idea like, for instance, if you think about animals, what do all animals have in common, right? So you define this abstract notion of animal, and then from that you inherit these mammals and reptiles. From mammals you have cows, cats, and dogs, etc. So, and another useful analogy here would be that when you go to a driving school, so you get a license for a particular type of vehicle, but not particular model of a car, right? So you learn general principles behind just how to drive that particular type of vehicle. So those are the major principles of object-oriented paradigm. And again, the core ideas here, the core concepts will be the class. So its class is this abstract entity, and object, which is instantiation of that particular class, right? So for instance, if you think about like integer numbers, right? So what do we have in the class? So we have the functionality to add them together, to subtract, to divide, etc. And what are those objects of the integer class? Those are particular values, right? 5, 3, 100, 1 million, etc. So how you define a class in Python? In order to define a class, you need to use the keyword class. So you use this keyword class, and then you provide the name of the class and the colon sign. So, and in this case, we create an empty class. We just use the special keyword pass. So it means that we create the class C, but it doesn't have anything in it. And then in order to create an object of that class, we basically just specify this class name, and we call this so-called constructor. So instead of class name, of course, we'll have the C, and we do not provide anything. There are no required parameters here. So we just sort of like call it as you would call a function. So, and then the result of this will be an object of that class, a particular instance. So here is an example of the class rectangle. So again, what do rectangles have in common? So they have the width and the height. So now you will notice some new function here. So this particular method with double underscore in front and double underscore as after. So this is called a magic method. So there are certain number of magic methods, and this is the most common one. So this method will be called automatically when you create an instance of the class. So whenever we create an object of the class rectangle, it will automatically call this method and will ask, we need to provide, what do we need to provide? The width of the particular rectangle and the height. In addition, you see there is an extra parameter called self. So self is the reference to that particular object. So whenever we create this object of the class, we don't really provide this self explicitly. So we only provide this width and height. So self will be generated for us. So it will be a reference to that particular object that we are currently creating. So inside of this method, we just say, OK, take this particular object that we are creating and assign width to whatever we provide here as an argument, and height also to the value that we provided here. This is called dynamic attribute. So those attributes will be specific to a particular object that we are creating. But we can also define so-called static attribute that is defined at the level of the class. For instance, we want to have all our rectangles to be green for some reason. So we'll provide the static attribute called default color, which is green. So whenever we create an object of the type rectangle, it will be green. But our object will vary in the width and height, right? Depending how we provided these values. So there are other magic methods that exist in Python. So one is called new. So it takes this class. So it's a method called to create a new instance of the class CLS. So init, the one that we just discussed, it's called after the instance has been created by this calling method new. And the del, which is called when the instance is about to be destroyed. So you can also look at this, follow this link to learn more about these magic methods. So now we can have a look at this particular class, file object. Here is an example of this initialization method, right? So what do we need to provide here? We ask the user to provide a file path and file name. And inside of this initialization, we take this reference to that particular object and take this property called file and assign it to the result of this open function. So we open this file and just provide this file object inside of our file property. And whenever we want to delete our object, so we can specify what needs to be done. So for instance, we can say that, OK, we need to close this file and then delete this particular property. So another thing that we need to discuss is these different methods. So there are methods that are specific for a class. There are methods that are specific for the objects. So so far, we just discussed these instance-related methods. But you can also define a method for the whole class that will operate on the level of the class. So for that, you will need to use so-called decorator, which is explicitly saying that this is a class method. So, and there's another decorator that is used for static methods. So typically, you use them for some auxiliary functions within the class. So let's do this toy experiment, creating a class called chess piece. So the class will just realize the functionality of different kinds of chess pieces. So, and as I mentioned before, we typically have some hierarchical structure. So how we introduce hierarchical structure in Python? So in order to introduce this, for instance, we would like to create this abstract class for chess piece, for abstract notion of chess piece. So we need to use the model called ABC. So ABC does not stand for alphabet, it stands for abstract base class. So there is a special module called ABC, and from that module, we import this abstract base class and the abstract method. So in order to define the abstract base class, we need to inherit our class from this ABC. So now the question is, what is abstract base class, right? So abstract base class is some special type of class for which we cannot create an object. So in which case we cannot create an object. In the case, for instance, when we define the interface, but we do not provide the full specifics, the full functionality. For instance, we can have so-called abstract method. We can just say that our chess pieces, we can move them, but they, as soon as, because we move them in a different way, depending on the type of this chess piece, we cannot define this yet. We just say there is such a functionality move, but we leave it empty. And in order to leave it empty, we say that this is abstract method. So we do not define how exactly we move this particular chess piece. So we just describe this sort of like interface, very abstract interface. And as soon as our class has at least one of such methods, it means we cannot create an object because we don't know what will be this functionality, how we should move this particular chess piece, right? So this is like this notion of abstract base class. Is it clear? So abstract base class is typically just used to define this interface in a very generic way. So, but there are some functions that we can still define. For instance, we can say there is a function, the method draw. So, and it just prints some message. And this message will be the same for all our inherited classes, the child classes. So, and again, in order to define this abstract base class, we need to inherit this from this ABC. Okay? So it means like when we create, so we define this abstract notion of a chess piece, and now suppose we want to create queen or king, right? We will inherit this queen or king from the chess piece, and automatically we'll have this method draw in them. We don't have to provide this again. So it will be inherited already. So here's just an example. Yeah, this is before we provide this example of how we inherit. Let's just first see that it will not work if we want to create an object of this abstract class. So if we try to, for instance, call the constructor chess piece, and put this result into A, it will give us an error because chess piece is an abstract class. Because, again, it has one of its methods as abstract method. We have not defined the full functionality yet. That's why we cannot create an object. So, but what we can do, so now, as soon as we define this general interface, we can take this interface and say that this will be a parent class for queen. So we say that queen is inheriting all the functionality and properties from chess piece. So, and inside of this queen, so we now required to define what it means to move. Because if you do not define this, you'll get an error. Because now you do not have this abstract base class, so queen is just the usual class, and you have to define how exactly you move this chess piece. Okay? So we will be required to specify this functionality. So, and in this case, for instance, we just say, okay, there's some print message moved from one position to another position. And now you can create an object of this queen class. And in addition to this method move, you will automatically have access to this public interface from the parent class. So we can call the method draw. So the method draw was defined over here. And because we inherit from this class, we also have access to all these public methods from that corresponding class. So that's pretty much it for today. So try to play with this example, and you can also look at this, the structure of these classes in Python library. You can explore this. Yeah, you can, for instance, create a toy structure of classes for, say, like animals. Try to think how you would conceptualize animals or geometric shapes. Okay, so that's it for today. It was a bit shorter, but hopefully you enjoyed the weekend. And I will see you here next week for the mid-semester test. So some of you will come here, some of you will be assigned to Wilson Hall, and there is another building, KL something. Anyway, you will have your location and seat assignment released on the 3rd of September. Okay, so, and I will see you here, some of you, not all of you, here for the mid-semester test.